The cosmos holds secrets that defy all logic. We are about to explore 25 of the most enigmatic events in interstellar space, mysteries that stretch from the edge of our solar system to the farthest reaches of the observable universe. By the end of this journey, you will confront cosmic puzzles that could rewrite the textbooks of physics and astronomy. We will examine a signal so powerful it was scribbled WW on a printout, and a star that dims in ways no natural law easily explains. Each event is a piece of a grander puzzle, a clue hidden in the dark. What does it truly mean to look into the profound unknown? Our journey into the interstellar unknown begins not with a whisper, but with a shout. On a quiet August night in 1977, a radio telescope known as the Big Ear was listening to the stars. It was a routine survey of the sky, a slow scan for any whisper of cosmic noise. Then, for exactly 72 seconds, the silence was shattered. The telescope recorded a narrowband radio burst so powerful, so perfectly tuned, that it was 30 times stronger than the background noise of deep space. The signal came from the direction of the constellation Sagittarius, and it matched the exact profile scientists had theorized an intelligent transmission would have. It did not drift, it did not waver. It was a pure, singular tone screaming across the cosmos. When astronomer Jerry Amon reviewed the computer printout days later, he saw the data represented as a string of letters and numbers. The intensity of the signal was so extraordinary that he circled the sequence in red pen and wrote one word beside it in the margin. Wow, that single, astonished exclamation gave the signal its legendary name. The printout itself, with its now famous sequence 6EQUJ5, became a holy grail of modern astronomy. It was a moment of pure, electrifying possibility. The search for a repeat began immediately and has never stopped. For decades, telescopes have been pointed back at that same patch of sky, listening with ever more sensitive ears. The silence that has followed is in its own way just as profound as the original signal. So what created that brief, brilliant flare? The leading natural explanation points to a comet. In 2017, a researcher proposed that two comets, which happened to be in that region of space at the time, could have generated a hydrogen cloud that the telescope detected. But this theory is heavily disputed. Many astronomers note that comets do not emit strong, narrowband radio signals like the one that was recorded. The signal's properties point toward something far more intriguing: an artificial origin. It was a beacon, perhaps from a civilization, momentarily pointing a powerful transmitter in our direction. A cosmic lighthouse whose beam swept over Earth for just over a minute and then was gone. The WOW signal stands alone, a solitary data point of immense significance. It is the ghost in the machine of our search for cosmic company, a reminder that the universe might be speaking. We just have to be listening at the right moment to hear it. That solitary shout from the cosmos was not alone for long. Decades after the WOW signal faded, a new and far more common cosmic scream began to echo across the universe, a phenomenon so energetic it defies belief. They are called fast radio bursts. For a few fleeting milliseconds, these events release more energy than our sun will emit in 80 years. Imagine the entire power output of a star compressed into a blink of an eye and broadcast across billions of light years. The first one was discovered only in 2007, hidden in archival data from a radio telescope in Australia. It was a single, brilliant spike, a cosmic flashbulb going off in a distant galaxy. For years, astronomers debated if it was even real or just some terrestrial glitch, but then they found another and another. Today, we detect them almost daily. The mystery lies not just in their staggering power, but in their behavior. Most are one-time events, a sudden, catastrophic explosion in the deep cosmos that is never seen again. But a crucial few are repeaters. The most famous, known as FRB 121102, fires off bursts from the same location in a dwarf galaxy over 3 billion light-years away. It chatters unpredictably, sometimes remaining silent for months before unleashing a storm of flashes. This repetition is a vital clue. It tells us the source is not destroyed in the blast, ruling out cataclysmic one-time events like the collision and merger of two ultra-dense neutron stars. So what cosmic engine can survive such a violent release of energy again and again? The leading suspect is a type of stellar corpse called a magnetar. These are neutron stars with magnetic fields so intense they are a quadrillion times stronger than Earth's. Think of a magnet so powerful it could strip the information from every credit card on the planet from halfway to the moon. Theorists suggest that starquakes on the surface of a magnetar, or sudden rearrangements of its unimaginably powerful magnetic field, could crack like a whip and produce these brilliant radio flashes. Yet even this extreme explanation is stretched to its limits by the most energetic bursts we see. This has led to more speculative ideas, including the notion of advanced technology. Some have proposed that beams used for powering light-sail spacecraft, vast structures designed to push interstellar vessels with pure light, could, from a cosmic distance, look exactly like a fast radio burst. While this is not the mainstream view, it highlights just how extraordinary these events are. But beyond their origin, FRBs have become unexpected tools for cosmic cartography. As these bursts travel across the universe, they pass through the sparse gas between galaxies. This material subtly slows and scatters the radio waves. By measuring this effect, astronomers can essentially weigh the invisible matter the burst has traveled through. Fast radio bursts are acting as probes, illuminating the universe's missing normal matter, material that has long been theorized but was nearly impossible to map. So each millisecond flash is a two-fold enigma. It is both a message about a violent, unknown event in a far-off galaxy, and a beacon that lights up the dark, invisible scaffolding of the cosmos itself. While bursts of radio energy flash and fade in milliseconds, another star in our galactic neighborhood has been performing a slow, mysterious dance of shadows. This is Tabby's star, officially catalogued as KIC 8462852, and its behavior is unlike anything else we have ever seen. Located over 1,000 light-years away in the constellation Cygnus, it was just another point of light in the data from the Kepler Space Telescope, an instrument designed to hunt for planets by spotting the tiny, regular dips in starlight they cause as they transit. But Tabby's star did not play by those rules. Astronomers, including citizen scientists from the Planet Hunters project, first flagged it because its dimming patterns were profoundly strange. Instead of the neat, predictable 1 or 2% dips caused by a planet, this star's light would sometimes plummet by a staggering 22%. That is not a planet, that is an enormous, irregular shape passing in front of the star, blocking a massive portion of its light. The dips were not periodic either. They came at irregular intervals, sometimes clustered together, sometimes with long periods of quiet. It was as if someone was turning a vast, celestial dimmer switch on and off at random. The most famous and tantalizing hypothesis to explain this bizarre behavior came from astronomer Jason Wright, who suggested we might be witnessing a partially constructed Dyson swarm. A Dyson swarm is a theoretical megastructure, a vast collection of orbiting solar panels or habitats built by an advanced civilization to capture a star's energy. Such a structure would not be a solid shell, but a ragged, uneven cloud of objects, casting complex and irregular shadows exactly like the ones we observed. This idea, often simplified as the alien megastructure hypothesis, captured the public imagination and propelled the star to fame. But science demands more than a compelling story. Astronomers immediately began searching for natural explanations. The first and simplest was a giant swarm of comets, perhaps stirred up by a passing star, creating a thick, dusty cloud that could intermittently block the light. Others pointed to circumstellar dust, debris from a catastrophic planetary collision, or even large, dark planetesimals surrounded by rings of material. More recent and detailed observations, particularly from the Spitzer Space Telescope, revealed that the star dims more in ultraviolet light than in infrared. This is a crucial clue. It tells us the material blocking the light is not solid, like an opaque megastructure, but is made of fine dust particles smaller than a grain of sand. Dust scatters shorter wavelength blue and ultraviolet light more effectively, which matches the observations perfectly. This evidence strongly favors a natural, if extraordinarily dramatic, explanation. The leading theory now suggests that Tabby's star is surrounded by a vast, uneven disk of dust and debris, possibly the remnants of a shattered moon or a catastrophically disrupted planet. The irregular dimming could be caused by giant clumps of this debris, along with a constant, fine haze orbiting in a chaotic cloud, yet the mystery is far from solved. What event could create such a colossal and messy debris field? Why is the dust not evenly distributed? The star itself also shows a very long-term, gradual dimming over the past century, adding another layer to the puzzle. The story of Tabby's star is also a landmark in how modern science is done. When professional observatory time to monitor the star grew scarce, the lead astronomer, Tabitha Boyajian, turned to the public. A Kickstarter campaign raised over $100,000, allowing a global network of amateur astronomers to purchase continuous time on a network of small telescopes. This citizen science project kept a constant watch on the star, catching its every flicker and ensuring the data kept flowing. So while the alien megastructure idea may be fading like one of the star's own dips, what remains is a profound and genuine cosmic mystery. It is a testament to the fact that the universe is still full of surprises, and that sometimes the most exciting discoveries begin when something simply refuses to behave as it should. The dust clouds around Tabby's star are a local mystery, but the next enigma arrived from a place utterly beyond our own. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. It was not on any predictable orbit within our solar system. Calculations confirmed a staggering truth: this object was not from here. It was the first confirmed visitor from interstellar space, and they named it Oumuamua, a Hawaiian term meaning scout or messenger from the distant past. As telescopes around the world swiveled to track it, the messenger revealed a series of bizarre traits that defied easy classification. First was its shape. By measuring how its brightness changed as it tumbled, scientists deduced it was not round like an asteroid or comet. Instead, it was dramatically elongated, perhaps 10 times as long as it was wide. Some described it as a cigar, others later as a flat pancake. This was an object with proportions never before seen in our solar system. The second shock was its motion. As Oumuamua sped away from the sun, it exhibited a slight but undeniable non-gravitational acceleration. It was moving just a bit faster than gravity alone could account for. For a normal comet, this is easily explained by outgassing. As the sun heats icy material, jets of gas act like tiny thrusters pushing the comet along. But Oumuamua showed no visible coma, the fuzzy cloud of gas and dust that surrounds an active comet. No tail was seen streaming behind it. It was dark, reddish, and seemingly inert, yet something was giving it an extra push. The scientific community scrambled for natural explanations. One compelling theory proposed it was a hydrogen iceberg. In the cold, dense cores of giant molecular clouds, solid hydrogen could form. As such an object neared the sun, the hydrogen would sublimate, providing the unseen thrust without creating a dusty coma. Another idea suggested a nitrogen iceberg, a chunk broken off from a Pluto-like world in another star system. The nitrogen would also vaporize cleanly, explaining the acceleration. Yet each model had its difficulties, requiring very specific and rare conditions to create such an object. Into this debate stepped Harvard astronomer Avi Loeb with a far more provocative hypothesis. He argued that the most straightforward explanation for the combination of characteristics, its extreme shape, its lack of outgassing debris, and its precise non-gravitational acceleration was that Oumuamua was a piece of advanced technology, specifically a light sail. A light sail is a thin, reflective sheet that uses the pressure of sunlight for propulsion, much like a boat sail uses wind. A discarded or derelict light sail tumbling through space would have the right flat, thin shape. The pressure of sunlight itself could provide the exact type of push we observed, with no need for visible outgassing. Loeb's suggestion, while controversial and not accepted by most astronomers, forced a crucial conversation about how we interpret anomalies. Should our default be to seek only natural explanations, even if they become increasingly complex? Or should we at least consider artificial origins for objects that fit no known mold perfectly? Regardless of where one stands on that debate, Oumuamua's legacy is undeniable. It was a cosmic wake-up call. We learned that interstellar objects pass through our solar system far more frequently than anyone had guessed. Its visit prompted the creation of new projects like the Vera-C, Rubin Observatory's legacy survey of space and time, which will scan the sky with such depth and frequency that finding the next Oumuamua will become routine. It taught us that our solar system is not an island, but a crossroads in a galaxy teeming with wandering material. The messenger from the distant past did not reveal its secrets easily, but its brief passage forever changed how we see our place in the stellar neighborhood. Oumuamua's silent passage forces us to confront a deeper, more unsettling question. If the galaxy is filled with such wanderers, and if the chemistry for life is sprinkled on comets and in nebulae, then where are all the builders? Why does the universe seem so profoundly, overwhelmingly silent? This is not a new question. It was posed bluntly over a lunchtime conversation in 1950 by the physicist Enrico Fermi. Looking at the staggering scale of the universe, the billions of stars older than our sun, he asked a simple, devastating question: where is everybody? The sheer math seems to promise an answer. Our Milky Way galaxy contains hundreds of billions of stars. Even if only a tiny fraction of those have Earth-like planets, and only a fraction of those develop life, and a fraction of that life becomes intelligent, the numbers still suggest the galaxy should be teeming with civilizations. We should see their probes, their signals, their vast engineering projects lighting up the night sky. Yet we see nothing but empty space and natural phenomena. This glaring contradiction between high probability and zero evidence is the Fermi paradox. One of the most compelling frameworks for answering it is the concept of the Great Filter. This idea suggests there is at least one enormous, perhaps insurmountable, barrier that prevents life from progressing from simple chemistry to a galaxy-spanning civilization. The terrifying part is we do not know where this filter lies. Is it behind us or ahead of us? If the filter is behind us, it means the step from non-life to simple, replicating cells is astronomically rare. Perhaps Earth won a cosmic lottery and we are utterly alone. This would resolve the paradox, but it is a lonely answer. The more haunting possibility is that the filter lies ahead. This means the transition from a technological civilization like ours to an interstellar one is the nearly impossible step. Perhaps every advanced culture eventually hits a wall. It could be self-destruction through nuclear war, runaway artificial intelligence, or ecological collapse. It could be a natural, unavoidable cosmic catastrophe, like gamma-ray bursts that periodically sterilize the galaxy. Or perhaps expansion itself is the trap. Maybe any civilization that reaches for the stars inevitably triggers something we cannot yet foresee. There are less dire possibilities too, often called soft filters. The zoo hypothesis proposes that advanced civilizations are out there, fully aware of us, but have chosen to place us in a kind of cosmic quarantine. They observe but do not interfere, allowing humanity to develop naturally, perhaps until we reach a certain maturity or technological threshold. It is a galactic prime directive. Another idea is that we are simply looking for the wrong things. Their technology or communication might be so advanced it is indistinguishable from natural physics to us, like an ant trying to comprehend the internet. Or perhaps interstellar travel is so slow and costly that every civilization turns inward, creating vast virtual realities instead of exploring the physical stars. Every enigmatic event we have discussed so far can be seen as a potential but deeply ambiguous data point in this grand paradox. The wow signal could have been a momentary ping from a civilization that quickly filtered itself out. Fast radio bursts could be the natural wreckage of those who failed. Tabby's star might show the ruins of a construction project abandoned when the builders vanished. Oumuamua could be the drifting artifact of a culture that never made it to the next stage. The silence is not empty. It is a canvas onto which we project our greatest hopes and our deepest fears. The Fermi paradox is more than a question about aliens. It is a mirror held up to humanity, asking what our own ultimate fate might be. Are we a unique miracle, a tragic flash in the pan, or simply one voice in a chorus that has not yet begun to sing? The search for an answer continues, listening intently to the quiet, hoping for a sound. This profound silence makes every subtle motion in the cosmos feel all the more significant. And one motion, detected at the very edge of everything we can see, threatens to shake the foundations of cosmology itself. It is called the dark flow. Picture the observable universe as a vast, expanding sphere of galaxies, all moving apart from each other in the aftermath of the Big Bang. This expansion should be smooth and uniform, like dots on an inflating balloon. But in 2008, a team analyzing data from the Wilkinson Microwave Anisotropy Probe satellite found something deeply strange. They were studying the cosmic microwave background, the faint afterglow of the Big Bang itself, which serves as a perfect backdrop to measure the motion of large structures. They tracked the movement of over 1,000 massive galaxy clusters and found they were not drifting randomly. Instead, these clusters, some billions of light-years apart, were all streaming in the same direction at an astonishing speed of over 2 million miles per hour. It was as if an immense, unseen hand was tugging on the fabric of the universe. This was not just a local effect. The flow appeared to extend to the very limits of our observational horizon, suggesting its source lay beyond it. The standard model of cosmology has no place for such a coherent, large-scale motion. Everything we see should be governed by the gravitational pull of matter within our own observable universe. The initial findings were met with intense skepticism. Could it be an error in the data or an unaccounted-for systematic effect? To settle the debate, scientists turned to a more advanced instrument, the Planck satellite. Its results, released years later, were ambiguous and fuel the controversy to this day. Some analyses of the Planck data seem to confirm a residual flow, though perhaps not as pronounced. Others argued the signal disappeared when different methods were used. The scientific community remains sharply divided. If the dark flow is real, its implications are staggering. The most extraordinary explanation is that the flow is caused by the gravitational pull of something truly outside our universe. Think of our cosmos as a bubble floating in a greater multiverse ocean. Another neighboring bubble universe with a colossal concentration of mass could be exerting a tidal force on our own, tugging at everything within our horizon. We would never see that other universe directly, as light from it could never cross the void between the bubbles, but we would feel its gravitational whisper. This idea challenges our most fundamental assumptions. It suggests our universe is not an isolated, self-contained entity, but part of a vaster, more complex structure we can only infer from its shadows. It turns the cosmic microwave background from a simple baby picture of our universe into a window, however smudged, into realms that by definition should be forever hidden from us. The dark flow, then, is more than a mystery of motion. It is a potential crack in the wall of reality, a hint that our cosmic map is missing its most important feature, the lands that lie beyond the edge. If the dark flow is a tug from beyond our cosmic horizon, then the great attractor is the undeniable pull from within it. This is not a distant theoretical force. It is a gravitational anchor, a colossal concentration of mass roughly 200 million light-years away in the direction of the constellations Centaurus and Norma. And it is dragging our entire galaxy, along with thousands of others, on a relentless journey toward it at over 1 million miles per hour. We are caught in a river of galaxies, all flowing toward a mysterious destination. For decades, the core of this anomaly was a profound frustration for astronomers. It lay directly behind the plane of our own Milky Way, a region so choked with stars, gas, and dust that we call it the zone of avoidance. It is like trying to see a distant city through a dense, brilliant fog. Our own galactic backyard was hiding the view. Early maps of cosmic motion revealed this immense pull, but the source remained shrouded. What could possibly have enough gravity to command the motion of so many galaxies? The first major breakthrough came when astronomers learned to see through the fog. Using instruments that peer in wavelengths of light invisible to our eyes, like X-rays and radio waves, they began to map the hidden landscape. They discovered that the great attractor is not a single, unimaginably dense object. It is a gravitational focal point, the center of mass for a vast collection of matter known as the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and it is a fitting name. This structure is our true cosmic address. It contains roughly 100,000 galaxies, including our own Milky Way, the Andromeda Galaxy, and the entire Virgo supercluster we once thought was our home. The Great Attractor sits at its heart, a massive knot in the cosmic web, but the story grew even larger. As surveys improved, astronomers realized that Laniakea itself is in motion. It too is being pulled. The source of that even greater tug is the Shapley supercluster, a staggering concentration of galaxies over 650 million light-years away. Shapley is one of the most massive structures known in the observable universe, so the picture that emerged is one of nested currents. Our local group of galaxies flows toward the Great Attractor, and that entire river of galaxies is itself flowing toward the even more immense Shapley supercluster. The Great Attractor, then, is not the ultimate destination, but a major waypoint on a far grander journey. It is a local overdensity, a hill in the gravitational landscape that we are rolling down toward a mountain range beyond. This recontextualization is a beautiful example of scientific progress. What began as a single, terrifying unknown, a devouring monster in the zone of avoidance, was revealed to be a complex and natural part of the universe's large-scale structure. The Great Attractor is a testament to the power of gravity to sculpt the cosmos over billions of years, weaving galaxies into filaments and sheets with vast, empty voids between them. We are not being pulled toward doom, but are participants in a slow, majestic dance that has been unfolding since the dawn of time. Yet, even demystified, it retains its power. It reminds us that our perspective is always limited. We had to learn to see in new ways to understand the force guiding our path. And it begs the question as we flow toward Shapley, what even greater structures lie beyond that, waiting to be discovered when we learn to see through the next cosmic veil? Gravity's grand currents shape galaxies, but sometimes the deepest mysteries are found in the smallest deviations. Our own robotic envoys, sent to explore the outer planets, began whispering a secret as they drifted into the void. The Pioneer 10 and Pioneer 11 spacecraft, after their triumphant flybys of Jupiter and Saturn, continued on their endless journeys out of the solar system. Mission controllers tracked them with exquisite precision, knowing their exact speed and trajectory. But by the early 1990s, a tiny, stubborn discrepancy emerged. Both spacecraft were slowing down slightly more than they should have been. The sun's gravity was pulling them back, of course, but there was an extra, constant deceleration, a tiny sunward tug equivalent to just 1/10 billionth of the gravity you feel on Earth. It was as if a faint, invisible hand was gently applying the brakes. This minuscule effect became known as the Pioneer anomaly. For over a decade, it was a persistent thorn in the side of physicists. The deviation was so small it could be dismissed as an accounting error, a rounding mistake in the complex equations of orbital mechanics. Yet it persisted in the data, a signal that refused to go away. When you have ruled out every known force gravity from the sun and planets, the drag of the solar wind, even the pressure of sunlight itself, and the anomaly remains, the mind turns to extraordinary possibilities. Could this be a signature of dark matter, a halo of unseen particles clustered in our solar system, exerting an extra gravitational drag? Or was it evidence of a flaw in our understanding of gravity itself? Perhaps Einstein's theory of general relativity needed a slight modification over vast interplanetary distances. Some even speculated it was an effect of the spacecraft's passage into a new, unknown region of space. The Pioneer anomaly became a classic example of a deep space mystery, a puzzle that seemed to point toward new physics. The resolution, when it finally came, was a masterclass in scientific humility and meticulous detective work. The breakthrough required thinking not about the cosmos, but about the spacecraft themselves. A team of researchers led by Slava Turishev embarked on a monumental effort. They recovered decades-old telemetry data, some from archaic formats, and even located original blueprints and fabrication notes to understand every bolt and component. They built a thermal model of the Pioneer spacecraft, tracing the intricate journey of heat. The source was the radioisotope thermoelectric generators, the nuclear power sources that provided electricity. These generators produced a steady flow of waste heat. The team realized this heat did not radiate away from the spacecraft uniformly. More heat was emitted from the rear of the craft, where the generators were mounted, than from the front. This anisotropic or directionally lopsided radiation acted like a tiny photon thruster. Every infrared photon carrying heat away from the back of the spacecraft gave it a minuscule push forward toward the sun. It was a constant, gentle pressure, exactly mimicking a sunward deceleration. When they painstakingly calculated this thermal recoil force and applied it to the trajectory models, the anomaly vanished. The mysterious hand was not a new force of nature, but the spacecraft's own warmth, patiently pushing back for decades. The story of the Pioneer anomaly is a profound lesson. It reminds us that the most tantalizing clues to rewriting the laws of physics can sometimes be found in the engineering details we brought with us. It celebrates the power of a mundane explanation, proving that a mystery solved is just as valuable as a mystery that endures, for it clears the path to see the next, real anomaly waiting in the dark. The warmth of the Pioneer spacecraft was a local effect, but the light from a distant star carries a much colder, more persistent secret. While the erratic dips of Tabby's star captured headlines, a deeper, slower mystery was unearthed from the vaults of astronomy's past. Researchers turned to the digital access to a sky century at Harvard, known as the Dash Archive. This is a collection of over 500,000 glass photographic plates, a century's worth of the night sky meticulously recorded long before digital cameras existed. By carefully digitizing and analyzing these fragile plates, scientists could measure the star's brightness going back to the 1890s. What they found was astonishing. Tabby's star did not just flicker erratically. Over the course of 100 years, from around 1890 to 1989, it steadily faded by a staggering 14%. This was not a quick dip. It was a long, slow sigh, a dimming that took a human lifetime to unfold. A star simply does not do that. Main sequence stars like our Sun are models of stability, burning with near-constant brightness for billions of years. A change of even 1% over a century would be monumental. 14% is off the charts. This discovery shattered any simple, one-off explanation. A giant swarm of comets could maybe cause the short-term dips, but it cannot account for a century-long, smooth decline. A catastrophic planetary collision could produce a lot of dust, but that dust would either dissipate or clump into planets on timescales far shorter than 100 years. Even the alien megastructure idea struggles here, as building a structure that large and that slowly over a century seems oddly paced and inefficient. The long-term dimming forces us to consider a more complex, multi-stage drama unfolding around this star. One compelling theory involves not one, but two separate populations of material. First, there could be a vast, uneven ring of debris, the remnants of a shattered planet or a violently disrupted asteroid belt. This ring contains the giant clumps and dense clouds that cause the dramatic, irregular dips we see today. But surrounding all of that, there might be a second, much larger and more diffuse cloud of ultrafine dust. This dust is not in clumps, but in a giant, hazy shroud that envelops the entire star system. Think of it like a star surrounded by a massive, lopsided veil. This veil is so thin it doesn't cause sharp dips, but it uniformly filters the starlight, causing that relentless century-long fade. The question then becomes, what created this two-tiered disaster zone? Perhaps a giant planet was torn apart by the star's gravity, creating an initial wave of large fragments. Later, collisions between those fragments over millennia could have slowly ground themselves into an all-encompassing fine powder. Or maybe the star itself is going through a rare and unstable phase, episodically belching out vast clouds of material that then settle into this complex architecture. The data from the old glass plates adds a crucial dimension of time, proving that whatever is happening to Tabby's star is not a momentary event. It is a process, a story that has been unfolding since the era of horse-drawn carriages and early telephones. It teaches us that some cosmic mysteries cannot be understood in a single snapshot. They require the patience to read the entire album, page by century-old page, listening for the slow heartbeat of a star in distress. The century-long dimming of Tabby's star was a powerful clue, but to truly understand what we were seeing, astronomers needed to look at the star in a different way. They needed to break its light apart to see what colors were missing and what colors were enhanced. This is the science of spectroscopy, and it would deliver a series of crucial verdicts on the most exotic theories. The first major test came from the Spitzer Space Telescope, which observes in infrared light the domain of heat. If a vast cloud of warm dust or a giant swarm of comets was blocking the star's visible light, that material should be absorbing sunlight and re-radiating it as infrared warmth. It would be like holding your hand near a hot stove. You feel the heat even if you cannot see the flames. Spitzer stared at Tabby's star with incredible sensitivity, searching for this telltale infrared glow. The result was definitive silence. There was no significant excess infrared heat. This single observation ruled out a major category of explanations. It meant there was no large, warm dust cloud enveloping the star. It also dealt a severe blow to the solid alien megastructure idea. A solid object like a giant solar panel or a rigid Dyson swarm component would absorb visible light and heat up dramatically, glowing brightly in the infrared. The lack of that glow suggested the blocking material was not a solid structure, but something else, something that did not retain heat well. This pointed strongly toward a very fine, cold dust, perhaps more like smoke than sand. But the mystery was not so easily solved. Another team of astronomers used a different, more subtle technique called polarimetry. When starlight scatters off dust particles, the light waves can become polarized, meaning they vibrate in a preferred direction. By measuring this polarization, scientists can learn about the size, shape, and distribution of the dust. their observations revealed something fascinating. The polarization changed during the star's dimming events. This was the smoking gun. It proved that the material causing the dips was indeed made of dust, and crucially, that this dust was not in a smooth, symmetric shell around the star. The changing polarization indicated the dust clouds were asymmetric, clumpy, and dynamic. They were moving, evolving structures passing in front of the star. So the picture that emerged from these spectral detectives was one of contradiction and complexity. We had fine, cold dust that did not glow in the infrared, yet it was arranged in large, uneven clouds that could block 22% of the star's light. This forced theorists to get creative. One leading model suggests the dust particles are incredibly small, smaller than particles in cigarette smoke. Such tiny grains have a huge surface area relative to their mass, so they radiate away any heat they absorb almost instantly, remaining cold and invisible to infrared telescopes. They are also excellent at scattering blue and ultraviolet light, which matches the observed color-dependent dimming perfectly. But how do such tiny particles stay around the star without being blown away by the pressure of starlight? They must be replenished continuously, perhaps from the collisions of larger, unseen parent bodies in a violent and chaotic debris disk. Each wavelength of light told a different part of the story. Visible light showed the dramatic dips. Ultraviolet light confirmed the dust was fine. Infrared revealed a puzzling absence of warmth. Polarization mapped the dust's lopsided shape. Together, they painted a portrait not of a single, simple catastrophe, but of an ongoing, messy process. The alien megastructure hypothesis, while a thrilling thought experiment, faded under this multi-spectral scrutiny. What remained was a natural, yet profoundly bizarre, circumstellar environment. Tabby's star became a laboratory for understanding how star systems can fall into chaos, how planets or moons might be destroyed, and how the resulting debris can behave in ways we are only beginning to model. It is a reminder that the universe does not need intelligence to build something that looks, to our limited first glance, utterly engineered. Sometimes nature's own ruins are strange enough to stop us in our tracks. The spectral secrets of Tabby's star pointed toward natural chaos, but the radio sky continued to broadcast its own, far more violent brand of mystery. Among the fleeting flashes of fast radio bursts, one source stood apart by breaking the most important rule. It came back, designated FRB 121102. This object was the first repeater ever discovered. Its location was pinpointed not just to a galaxy, but to a tiny, turbulent dwarf galaxy over 3 billion light-years away. This was a crucial clue. Dwarf galaxies are often considered cosmic factories for intense stellar activity, places where stars form and die in frantic cycles. Even more intriguing, the repeating bursts were found to be associated with a persistent, much weaker radio source, like a faint, steady hum beneath the occasional deafening scream. This hinted at a permanent engine, a powerhouse capable of surviving its own apocalyptic outbursts again and again. For years, the leading suspect for this engine was a magnetar, a type of neutron star with a magnetic field so unimaginably strong it could twist the fabric of space around it. The theory was elegant: a starquake on the magnetar's crust or a sudden snapping and reconnecting of its magnetic field lines could unleash a catastrophic blast of energy focused into a beam, which we would see as a brilliant radio flash. But it remained a theory based on distant extragalactic evidence. Then, in April 2020, the mystery came home. Within our own Milky Way, a known magnetar called SGR 1935+2154 woke up. It emitted not just its usual X-ray bursts, but a simultaneous, incredibly bright millisecond radio burst. For the first time, we had a front-row seat to a fast radio burst being born. The energy was millions of times greater than any radio pulse ever seen from a galactic object, yet it was still thousands of times weaker than the extragalactic FRBS. This was the smoking gun. It proved conclusively that at least some fast radio bursts, including the powerful non-repeating kind, could be produced by magnetars. The difference in power likely comes from distance and environment. An extragalactic magnetar in a young, dense nebula of its own making could have its explosive energy amplified as it plows through that surrounding material, creating a far brighter flash. So we had an answer, but as often happens in cosmology, it opened new and more subtle questions. If magnetars can produce both repeating and one-time bursts, what determines the difference? Why does FRB 121102 chatter unpredictably for years, while others fire once and go eternally silent? The answer may lie in the magnetar's surroundings and its age. A young magnetar, still embedded in the dense debris of the supernova that created it, might have a chaotic environment that triggers repeated outbursts. An older magnetar, having cleared its neighborhood, might only produce a cataclysmic burst during a rare, singular event like a colossal starquake that fundamentally cracks its structure. Or perhaps the distinction is in the magnetic field itself. Some magnetars might have fields so complex and unstable they are prone to frequent ruptures, while others build up tension for millennia before a single, catastrophic release. The repeating bursts, then, are not necessarily a different kind of object. They might simply be a different phase in a magnetar's violent life, a tantrum-prone youth versus a quiet maturity that ends in one final, spectacular shout. This realization transforms these cosmic explosions from isolated curiosities into chapters in a stellar biography. Each flash, whether a solo performance or part of a series, tells us about the death throes of a star, the physics of the most powerful magnets in the universe, and the turbulent nurseries that shape their explosive lives. The enigma is no longer what they are, but understanding the precise, unforgiving conditions that make them speak. The violent tantrums of magnetars shape galaxies, but an unseen sculptor is responsible for the galaxies themselves. This sculptor is dark matter, the most profound and pervasive enigma in all of interstellar space. It is not a single event, but the silent background against which every cosmic drama plays out. We know it is there because of what it does. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies, expecting stars on the outer edges to move slower than those near the bright center, just as Pluto orbits the Sun more slowly than Earth. What she found was astonishing. Stars at the very fringe of galaxies were whipping around just as fast as those near the core. According to the laws of gravity, these galaxies should be flying apart. The only way to hold them together was to postulate a vast, invisible halo of mass surrounding each galaxy, a halo that does not emit or reflect any light. This was the first strong evidence for dark matter. The clues multiplied. When we look at massive galaxy clusters, we see them acting as gravitational lenses. Their immense gravity bends the light from even more distant galaxies behind them, distorting and magnifying their images into arcs and rings. By measuring this distortion, astronomers can map the cluster's total mass. The result is always the same. The visible stars and hot gas account for only a small fraction of the gravity required to create such a lens. An enormous amount of invisible mass must be present, warping the fabric of space itself. Finally, the pattern of tiny temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, acts as a cosmic ledger. It tells us precisely how much normal matter, dark matter, and dark energy the universe contains. The ledger is unequivocal. All the atoms that make up stars, planets, and us constitute less than 5% of the cosmos. Dark matter makes up about 27%. It is the universe's dominant architectural material. So what is it? We know what it is not. It is not black holes, at least not in large numbers. Precise observations rule them out as the primary component. It is not any form of normal matter made of protons and neutrons because it does not interact with light at all. It is something entirely new. the leading candidate for decades has been a theoretical particle called a weakly interacting massive particle, or a WIMP. As the name suggests, these particles would have mass, making them feel gravity, but they would interact with normal matter only through the weak nuclear force and gravity, passing through our planet as if it were a ghost. Billions might be streaming through your body every second, utterly unnoticed. To catch one, physicists have built exquisitely sensitive experiments in deep underground mines where they are shielded from cosmic rays. They use vats of ultra-pure liquid xenon or other materials, waiting for the once-in-a-universe event where a dark matter particle might bump into an atomic nucleus and produce a tiny flash of light or a minute charge. So far, the detectors have remained silent. This absence has breathed new life into a radical alternative, that we do not need dark matter at all, but a modification to our laws of gravity. The theory called modified Newtonian dynamics, or MUND, proposes that gravity behaves differently at the extremely low accelerations found at the edges of galaxies. It can perfectly reproduce galaxy rotation curves without any invisible matter. For many years, MUND was a compelling underdog theory, but it has struggled to explain all the evidence, particularly the gravitational lensing by galaxy clusters and the detailed patterns in the cosmic microwave background, which strongly favor the existence of a separate particle-based dark matter. The debate, however, is far from settled. Each new, deeper, quieter detector that fails to find a WIMP makes the mystery more profound. We are left with a universe where the vast majority of matter is a substance we cannot see, touch, or currently detect. A substance that built the cosmic web upon which galaxies are strung like beads on a string. It is the ultimate interstellar enigma, the shadow skeleton of reality itself. The shadow skeleton of dark matter weaves the cosmos into a vast, intricate web. But within that web there are holes, and one hole is so vast it defies comprehension. This is the Boötes Void, a spherical region of space roughly 330 million light-years across. To grasp that scale, if you placed our Milky Way at one edge, you would need to travel for over 300 million years at the speed of light to reach the other side. Within this incomprehensible volume, astronomers expected to find thousands, perhaps tens of thousands of galaxies. Instead, they have found only a few dozen. It is a cosmic desert of staggering proportions, a place where the universe's grand design seems to have failed. Such voids are a natural part of the universe's large-scale structure. After the Big Bang, slight irregularities in density were amplified by gravity over billions of years. Dense regions attracted more matter, growing into the filaments and clusters of the cosmic web. The less dense regions were left behind, emptying out as matter flowed toward the gravitational hills. The Boötes Void is simply an extreme example of this process, a valley so deep and wide it feels unnatural. Its existence forces a profound and unsettling question. Is this emptiness a statistical fluke, a 1 in a trillion chance in the cosmic lottery, or does it point to a gap in our understanding of how structure forms? The sheer size of the void pushes the limits of our best cosmological models. It is almost too big to exist, yet within this great nothing there are islands. A handful of galaxies stubbornly cling to existence in the void. One of the most famous is a spiral galaxy catalogued as MCG plus 01020015. Astronomers call it the loneliest galaxy in the universe. From its perspective, the night sky would be almost black. If you lived on a planet in that galaxy, you would look out and see only a handful of other galactic pinpricks in the immense dark. The nearest major galaxy cluster would be so far away its light would be faint and ancient. This isolation makes void galaxies like it priceless laboratories. How does a galaxy form and evolve when it is cut off from the cosmic mainstream? In the crowded environment of a cluster, galaxies are constantly interacting, merging, and having their gas stripped away, which shapes their size and star formation. But a void galaxy grows in solitude. Its gas reservoir remains largely untouched, allowing it to form stars at its own quiet pace for billions of years. Studying these isolated systems helps astronomers disentangle the internal processes of galaxy life from the violent influence of the environment. They are the cosmic equivalent of a child raised in complete seclusion, revealing what is innate to a galaxy's nature. The Boötes void, therefore, is more than an empty space. It is a boundary condition for the universe. Its profound emptiness tests the limits of our theories of cosmic evolution, while the few galaxies within it act as control experiments in the study of galactic life. It stands as a monument to the fact that the universe is not just a tapestry of light, but also a canvas of profound and meaningful shadow. The profound emptiness of voids like Boötes stands in stark contrast to the crowded, violent cores of our own cosmic neighborhood. There, a silent feast of epic proportions has been underway for billions of years. Our Milky Way is not a peaceful island universe, but a predator. It engages in a process astronomers call galactic cannibalism, where large galaxies like ours tear apart and absorb smaller dwarf galaxies that venture too close. This is not a quick, explosive event, but a slow, gravitational dismemberment played out over cosmic eons. The victim stars are stripped away, drawn into long, shimmering streams that orbit the larger galaxy, eventually becoming indistinguishable from its own population. We are surrounded by the ghostly remnants of these ancient meals. A prime example is happening right now in our own galactic backyard. The Sagittarius dwarf spheroidal galaxy is a small satellite of the Milky Way, and it is in its death throes. As it orbits, our galaxy's immense gravity pulls at it like tides on a fragile moon. With each pass, the dwarf galaxy is stretched and torn. Its stars are being siphoned off into two magnificent, opposing streams that wrap around the entire Milky Way, a celestial ribbon of stolen light. In a few more orbits, perhaps 100 million years, the core of the Sagittarius dwarf will be completely dissolved. Its stars will join the Milky Way's halo, and only these faint streams will remain as a tombstone, a fossil record of a galaxy that was. But this gravitational violence has another, more spectacular consequence. In the chaotic dance of a merger or a close encounter, individual stars can be slingshotted with unimaginable force. These become hypervelocity stars, projectiles flung from the galactic gravitational well at speeds over 1 million miles per hour. For a long time, the leading theory for their origin involved a dramatic scenario at the very heart of the galaxy. Imagine a binary star system, two stars orbiting each other, wandering too close to the supermassive black hole at the Milky Way's center. The black hole's gravity can capture one star, pulling it into a tight orbit, while violently ejecting its companion like a stone from a sling. This ejected star will be given a tremendous kick, sending it racing out of the galaxy on a one-way trip into intergalactic space. This theory moved from speculation to stunning confirmation with the discovery of a star named S5HVS1. Traveling at about 4 million miles per hour, it is one of the fastest stars ever detected. By tracing its path backwards across the sky, astronomers found its trajectory leads directly back to the galactic center, a perfect match for the black hole slingshot mechanism. This star is a runaway, an exile cast out by the most powerful engine in the galaxy. It will eventually leave the Milky Way behind, destined to wander the dark between galaxies forever, a lonely traveler born from an encounter with a monster. Galactic cannibalism and its hypervelocity offspring reveal a universe of dynamic, often violent, relationships. They show us that galaxies grow not just by forming new stars, but by consuming their neighbors. And in that chaos, they can accidentally create celestial bullets, stars given a freedom so absolute they abandon their galactic home entirely. These processes remind us that the serene spiral we see on a clear night is in truth a scene of constant, slow-motion transformation, where even the stars themselves can become refugees or prey. Yet even a hypervelocity star is a pebble compared to the cosmic bullet discovered streaking across the void in 2023. The Hubble Space Telescope captured something unprecedented, a supermassive black hole with the mass of 20 million suns hurtling through intergalactic space. It was not sitting quietly at the heart of a galaxy. It was running, and behind it, it was drawing a brilliant line of newborn stars across the darkness. The image is startling. A thin, straight streak of intense blue light over 200,000 light-years long connects a distant galaxy to the rogue black hole like a taut umbilical cord. This was not a jet of superheated material which we often see from active black holes. This was a trail of star formation. The theory that explains this spectacle is as violent as the image suggests. It begins with a galactic merger. When two galaxies collide, their central supermassive black holes eventually sink to the new combined core, forming a binary pair. They orbit each other, slowly losing energy. But if a third galaxy with its own black hole joins the chaotic dance, the three-body interaction becomes unstable. In a gravitational game of cosmic pinball, one of the black holes can be flung out at tremendous speed. This is precisely what astronomers believe happened. The ejected supermassive black hole, still surrounded by a dense cloak of gas from its former home, shot away like a cannonball. As it plows through the tenuous gas that exists between galaxies at millions of miles per hour, the gas is compressed and shocked along its path. This compression triggers collapse, igniting the birth of stars directly in the black hole's wake. Think of it as a celestial plow, furrowing the barren intergalactic medium and sowing seeds of starlight as it goes. This discovery shatters several quiet assumptions. First, it proves that supermassive black holes can indeed be forcibly ejected from their galaxies, something theorized but never before observed with such clarity. Second, it reveals that black holes are not just destructive engines. In their wake, they can be accidental creators, midwives to stellar nurseries in the most unexpected of places. The star trail is too long and too straight to have been formed by any other known process. It is a forensic mark, a skid mark on the cosmos, pointing directly back to a catastrophic event of unimaginable force. This black hole bullet forces us to revise our models of galactic evolution. It demonstrates that the aftermath of galaxy mergers is not always a neat, settled core. It can be chaotic and explosive, with the very anchors of galaxies becoming projectiles. It asks a profound question. How many other runaway giants are speeding through the darkness, invisible to us because they have left their luminous trails behind or have not yet entered a gas cloud to light their path? This single streak of blue is a snapshot of a universe in motion, where the most massive objects can become fugitives and where creation follows closely on the heels of the most violent expulsion. A runaway black hole seeds stars in its wake, but some survivors of cosmic violence are transformed into something far more strange and precious. Deep within the constellation Serpens, a dead star spins over 10,000 times every minute, emitting a metronome-perfect beam of radio waves. This pulsar, known as PSRJ 1719-1438, holds a secret in its gravitational embrace. Orbiting it, completing a revolution in just 2 hours and 10 minutes, is a world unlike any other in our catalogues. Astronomers call it PSRJ 1719-1438b, but its popular name captures the imagination more directly: the Diamond Planet. This world was not found by watching for a star's dimming light, but by listening to the impeccable clockwork of a pulsar. As the planet orbits, it gives the pulsar a tiny gravitational tug, causing the rhythm of its radio pulses to arrive at Earth a fraction of a second early or late. From these minuscule timing variations, astronomers could deduce the planet's mass and orbit. The data revealed something astonishing. The planet is incredibly dense, with a mass slightly greater than that of Jupiter, yet it is compressed into an object only about half of Jupiter's width. Such density points to a composition not of hydrogen and helium like gas giants, but of crystalline carbon and oxygen. Under the immense pressures of this compact world, the carbon has likely crystallized into a structure akin to diamond. Imagine a world where the very ground beneath your feet, the mountains, and the core are, in essence, a single planet-sized gem. The existence of this glittering relic tells a story of catastrophic stellar evolution. The system began as a binary pair of stars. The more massive one exploded as a supernova, leaving behind the ultra-dense, rapidly spinning neutron star we now see as the pulsar. The companion star, meanwhile, aged into a red giant and then a white dwarf, a hot, Earth-sized core of carbon and oxygen. As the two dead stars drew closer, the pulsar's intense gravity began to siphon material from the white dwarf, a process that also spun the pulsar up to its incredible speed. Eventually, the white dwarf was stripped down past its minimum mass, unable to sustain the nuclear reactions in its core. What remained was its naked, crystalline heart, the diamond planet we detect today. This world is a monument to stellar cannibalism and survival. It is the ghost of a star, its body vaporized, leaving only its dense, crystallized core to circle the vampire that consumed it. The diamond planet is not a hospitable place. Bathed in intense radiation from its pulsar companion, its surface would be sterile and hostile. Yet, as a scientific object, it is a jewel. It proves that planetary systems can form from the ashes of stellar death and survive the most violent phases of a star's life. It expands our understanding of what a planet can be, not just a rocky sphere or a gas giant, but the fossilized core of a once proud sun, forever orbiting the beacon of its own destruction. At the heart of our galaxy, a silent, invisible fire burns. The Fermi Gamma Ray Space Telescope orbiting Earth has mapped the sky not in visible light, but in the most energetic form of radiation, gamma rays. When scientists compiled its data from the galactic center, they expected a certain level of background gamma radiation from known sources, like supernova remnants and pulsars. But the map revealed something startling, a vast, diffuse glow of excess gamma rays concentrated in the region around the Milky Way's core. This glow, known as the galactic center excess, is an unexplained surplus of energy, a beacon shining in a spectrum our eyes cannot see. The shape of this emission is particularly intriguing. It is symmetrically distributed around the galactic center, fading away smoothly with distance. This spherical halo of gamma rays is exactly the kind of signal theorists predicted for one of the universe's greatest mysteries, dark matter. According to leading models, dark matter particles could be their own antimatter opposites. If two of these particles were to collide in the dense heart of the galaxy, they would annihilate each other in a flash of pure energy, producing gamma rays. The smooth, round shape of the excess matches the predicted distribution of a dark matter halo perfectly. It was as if we had finally caught a glimpse of the shadow skeleton of the universe, not through gravity but through its self-destruction. The possibility sent a wave of excitement through the physics community. Could this be the first direct detection of dark matter particles, not in a lab deep underground, but in the wilds of interstellar space? Yet, extraordinary claims require extraordinary evidence, and the cosmos is a place of many overlapping signals. Astronomers quickly proposed more conventional, if still exotic, explanations. The leading alternative points not to an exotic particle but to a celestial choir. The galactic center is a crowded, ancient place, likely teeming with thousands of millisecond pulsars. These are neutron stars that have been spun up to incredible speeds, emitting beams of radiation including gamma rays. Individually, they are too faint and close together for Fermi to resolve as distinct points of light. But collectively, their combined, unresolved glow could mimic the smooth, spherical excess we observe. It would be like standing far from a city at night. You see a general glow, not the individual streetlights. Another theory looks to the past activity of our galaxy's central supermassive black hole, Sagittarius A star. While it is quiet now, it may have been far more active in the past, accelerating particles to near light speed. The remnants of those ancient outbursts, particles still swirling and colliding in the central region, could also produce the observed gamma-ray haze. So we are left with a classic cosmic detective story. Is the signal the long-sought fingerprint of dark matter annihilation, a discovery that would revolutionize physics? Or is it the collective murmur of countless dead stars, or the fading echo of the black hole's ancient roar? Each interpretation has its strengths and weaknesses. The dark matter explanation elegantly fits the shape, but requires a specific type of particle with just the right properties. The pulsar explanation is more mundane, but we would need to explain why so many of them exist in just the right distribution to create such a smooth glow. For now, the galactic center excess remains a tantalizing, unresolved clue. It is a reminder that the universe often speaks in whispers and hints, and that the most profound truths can be hidden in the background static of the cosmos, waiting for the next, more sensitive instrument to finally tell us what we are truly seeing. That mysterious gamma-ray glow from the galactic center is a signature written in pure energy, but some of the cosmos's most profound secrets are painted with a far more delicate brush. Drifting through the constellation Monoceros over 2,000 light-years from Earth is a celestial masterpiece known as the Red Rectangle Nebula. Through a telescope, it does not look like the chaotic, billowing clouds of most nebulae. Instead, it appears as a stunning, geometrically perfect structure, a vivid red rectangle with dark, X-shaped rungs, like a cosmic ladder or an immense, glowing jewel box set against the velvet of space. The central star, HD 44179, is not one but two. It is a close binary system where a dying star, having exhausted its hydrogen fuel, is expelling its outer layers into space. Its companion star orbits incredibly close, shaping this outflow into something extraordinary. The stellar winds and radiation from this pair do not expand in a simple sphere. They collide and are funneled into two opposing cones or lobes, creating the classic bipolar shape we see. Our view from Earth looks directly down the barrel of one of these cones, with the thick dust lane of the star's equator blocking the center, giving us the illusion of a hollow rectangle. But the true enigma is the ladder. Those precise, dark X-shaped spikes within the glowing red gas are not an artifact of the image. They are real features, concentric rings of dust that look like rungs due to our perspective. They are thought to be created by periodic eruptions from the binary system, ejecting material in pulses every few hundred years. Each pulse creates a new shell of dust, and as these shells expand, we see them edge on, forming the lines of the ladder. The vivid red color itself is a clue, emitted by hydrogen gas excited by the intense ultraviolet light from the hot central stars. Yet for all its beauty and our detailed understanding of its components, the red rectangle retains a core mystery. The perfection of its symmetry, the crispness of its angles, and the precise regularity of its dust rings push our models of stellar wind interactions to their limits. The complex dance between the two stars, their magnetic fields, and the physics of how dust condenses in those outflows is not fully understood. It is a reminder that even when we know the players' binary stars, stellar winds, and dust, the choreography of their final performance can produce results of breathtaking, almost artificial precision. This nebula is not a relic of a violent explosion, but a slow, elegant exhale, a star system writing its final chapter in glowing gas and shadow. It shows us that the universe's artistry is not limited to grand cataclysms. Sometimes, its most haunting puzzles are those crafted with the utmost patience and grace. The geometric perfection of the red rectangle is a human-scale marvel, but some of the cosmos's most powerful art is painted not with light but with shadow. High above the southern hemisphere, nestled beside the brilliant stars of the Southern Cross, lies a profound absence. This is the Coalsack Nebula, a vast, irregular blot of darkness that seems to tear a hole in the starry fabric of the Milky Way. It is not a void like the Boötes region. It is something far more substantial and closer to home. The Coalsack is a dark nebula, an immense cold cloud of interstellar dust and gas so dense it completely obscures the light from the millions of stars that lie behind it. To our eyes, it appears as a featureless black patch, a cosmic silhouette, but this darkness is not empty. It is a cocoon. Within that frigid, pitch-black cloud, hidden from visible light, the raw materials of new solar systems are slowly, silently coming together. The temperatures inside can plummet to just a few degrees above absolute zero. In that profound cold and under the gentle crush of gravity, microscopic dust grains of carbon and silicate begin to stick together. Hydrogen molecules gather. Over millions of years, these pockets of density grow, collapsing under their own weight, their cores heating until nuclear fusion ignites. The Coalsack and countless dark nebulae like it are stellar nurseries. The very darkness we see is the womb from which stars are born. Eventually, the fierce radiation and stellar winds from those newborn stars will blow away the obscuring dust, revealing the brilliant clusters within, and the nebula itself will seem to dissolve. For now, it stands as a reminder that the universe's greatest acts of creation often happen behind the darkest curtains. This interpretation of the Coalsack as a place of potential, however, is a very modern scientific reading. For the indigenous peoples of Australia who have observed this patch of sky for over 65,000 years, the Coalsack Nebula is not an absence at all. It is a vital, defining feature in one of the most important constellations in their celestial mythology. They do not see the Emu as a pattern of stars, but as a pattern of the dark spaces between them. The Coalsack forms the head of the Emu in the sky. The dark dust lanes running along the Milky Way, our galaxy's own spine, form its long neck and bulky body. This is a constellation defined not by points of light, but by the shape of the shadow. The Emu is a deeply significant figure, its appearance in the sky tied to seasons, animal behavior, and cultural lore. When the Emu appears high in the night sky, its body stretched along the Milky Way, it signals the time when real emus are laying their eggs. This celestial storytelling transforms the Coalsack from a mere hole in the sky into a character in an epic, living narrative written across the heavens. It represents a fundamentally different way of seeing. Where Western astronomy traditionally connected the dots of light, indigenous Australian astronomy connected the spaces between them, reading meaning into the darkness itself. The Coalsack, therefore, holds a dual enigma. It is a physical mystery, a dense cloud hiding the mechanics of star birth, and it is a cultural one, a testament to the human mind's profound need to find pattern, story, and connection in the cosmos, whether illuminated by starlight or defined by its absence. It asks us to look at the sky again, to wonder what other stories are written in the shadows we have learned to overlook. That darkness is a canvas for creation, but some of the universe's most violent art is painted with the light of its own destruction. In the constellation Cassiopeia, a cosmic ghost haunts the sky. This is the supernova remnant Cassiopeia A, the youngest known in our Milky Way, the glowing wreckage of a star that exploded roughly 340 years ago. For decades, telescopes have mapped its intricate structure, a tangled web of shock-heated gas glowing in X-rays and radio waves, expanding at millions of miles per hour. But in 2023, the James Webb Space Telescope turned its infrared eye toward this chaos and saw something entirely new, something hidden from every other instrument. Nestled within the remnant's fiery heart was a strange, wispy structure glowing with an eerie, translucent green light. Astronomers named it the Green Monster. This was not part of the main debris field from the supernova blast. The green monster is a fossil, a delicate shell of material that tells a story from long before the star's final cataclysm. Analysis revealed this ghostly structure is composed of material the doomed star violently ejected tens of thousands of years before it went supernova. In its final millennia, the massive star became wildly unstable, convulsing in a series of titanic eruptions. It shed layers of its own atmosphere into space, creating a vast, expanding bubble around itself. Then, when the core finally collapsed and the supernova detonated, the unimaginable shockwave from that explosion slammed into this pre-existing shell. The James Webb Telescope captured that moment of impact frozen in time. The green monster is that ancient shell, now illuminated and shredded by the supernova's fury glowing from the collision. This discovery fundamentally changes the narrative of a star's death. We used to think of a supernova as a single, definitive event, a star shining steadily, then suddenly exploding. Cassiopeia as ghost reveals a far more dramatic and protracted final act. The star was a ticking bomb, and its final countdown included violent previews of the devastation to come. It spent its last millennia in a state of eruptive turmoil, heaving vast quantities of its own substance into the void. This pre-explosion activity shapes everything about the remnant we see today. It determines how the debris expands, how the shock waves propagate, and how elements forged in the blast are mixed and scattered into interstellar space. The green monster is a time capsule, allowing us to read the star's final diary entries written in glowing gas from an era long before the main event. Studying this ghost is like having a before and after picture of a cosmic catastrophe. By understanding the structure and composition of this pre-existing shell, astronomers can work backwards to model the star's final, unstable breaths. How much mass did it lose? What was the speed and timing of those eruptions? The answers rewrite the textbook on the life cycle of the most massive stars. They show us that the stage for cosmic destruction is set millennia in advance, and that the echoes of a star's death include whispers from its turbulent, pre-explosive life. The green monster is not just a beautiful, eerie feature. It is a revolutionary clue, forcing us to listen to the whole story of a star's end, not just its final, thunderous shout. The ghostly shell of Cassiopeia is a monument to stellar death, but what if we looked for monuments to life on a far grander scale? The search for alien intelligence has long moved beyond listening for radio signals. Today, a key part of the hunt involves looking for the unintended byproducts of cosmic-scale engineering, the waste heat of a civilization that has learned to harness the power of its sun. This is the search for Dyson spheres, a concept first proposed by physicist Freeman Dyson in the 1960s. Dyson reasoned that any energy-hungry, advanced civilization would eventually need to capture most of the light from its home star. They might build a vast swarm of orbiting solar collectors, a structure that would completely enclose the star. While the visible light from that star would be blocked, the structure itself would absorb that energy and re-radiate it as waste heat in the form of infrared light. From a great distance, such a star would appear strangely dim in visible light but would glow brightly in the infrared, a cold, dark object radiating a telltale warmth. It is a search for the thermal fingerprint of a god-like project. This is not just speculative fiction. It is a core part of the scientific search for technosignatures, physical evidence of technology. One of the most systematic efforts to find such fingerprints was the Glimpsing Heat from Alien Technologies survey, known as GHT. This project used data from NAS, a wide-field infrared survey explorer satellite, to scan the entire sky, analyzing the infrared signatures of around 100,000 galaxies. The goal was to look for galaxies where an unusually high fraction of the total starlight had been converted into mid-infrared waste heat, a sign that a vast number of stars might be partially enclosed. The results were both fascinating and humbling. The GHT survey found no evidence of galaxies completely dominated by such heat. the universe, at least on a galactic scale, does not appear to be crawling with Type 3 civilizations that have harnessed the energy of every star. However, the survey did identify a handful of individual objects, about 50 in total, that showed unusual infrared excesses worthy of further study. These are not confirmed Dyson spheres. They are simply anomalies, objects whose infrared glow is higher than current astrophysical models can easily explain. Each candidate requires careful follow-up to rule out natural causes. Many turned out to be stars shrouded in thick, warm dust from recent collisions or prolific planet formation. Others were galaxies with intense bursts of star formation, where vast clouds of dust are heated by newborn stars. So far, every unusual signature has found a plausible, if exotic, natural explanation. Yet the search continues and evolves. Newer surveys now look for partial Dyson swarms, structures that might block only a percentage of a star's light, creating more subtle infrared mismatches. The key is to find an object that is strong in the mid-infrared but shows absolutely no signs of the warm dust that should accompany it. A star that is paradoxically clean yet glowing with waste heat. This rigorous process of proposing an extraordinary idea and then systematically trying to disprove it with natural explanations is the very heart of good science. It refines our understanding of what is truly anomalous. The search for Dyson spheres, therefore, does more than scan for alien engineers. It forces us to better understand the infrared sky, to catalog all the strange and wonderful ways nature itself can mimic the signatures we once thought belonged solely to intelligence. It is a search that, regardless of its ultimate answer, deepens our map of the cosmos, teaching us to read the faint, warm whispers of the universe with ever more discerning eyes. That search for cosmic intelligence, for the waste heat of unimaginable projects, began with a far more humble and startling discovery. In the quiet English countryside of 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a new radio telescope she had helped build. The instrument, a forest of wooden poles and wires covering 4.5 acres, was designed to study distant quasars. But as Bell Burnell pored over the paper chart recordings, she noticed a peculiar bit of scruff, a faint, pulsing signal that appeared and disappeared with the rotation of the Earth. It was not the smooth hiss of a quasar, it was a series of sharp, precise ticks. She marked the anomaly with a question mark in red pen. Weeks later, she found it again. This time, the signal was clearer and its regularity was breathtaking. It pulsed once every 1.337301113 seconds with a metronome's unwavering precision. The rhythm was so exact, so artificial seeming that the only conceivable source, at least to the human mind confronting the unknown, was intelligence. The team jokingly labeled the source LGM1 for Little Green Men. It was a half-serious, half-awestruck designation for what seemed to be a beacon. Here was a signal from deep space that did not drift, waver, or fade. It was a perfect cosmic clock ticking away in the constellation Vulpecula. The implications were staggering. Had they truly stumbled upon a lighthouse built by an alien civilization? The scientific process, however, demands skepticism even of one's own most thrilling hopes. Before announcing the discovery of extraterrestrial intelligence, the team had to exhaust every natural explanation. The signal was too fast for a white dwarf star to produce. It was too regular for any known variable star or quasar. The breakthrough in understanding came with the detection of a second, similar signal from a completely different part of the sky. The odds of two separate civilizations deciding to beam identically structured pulsars at Earth were vanishingly small. The source had to be natural. The answer, when it crystallized, was a revelation that reshaped astrophysics. The pulsars were not a message, but the lighthouse beam of a rapidly spinning neutron star. When a massive star dies in a supernova, its core can collapse into an object so dense that a teaspoon of its material would weigh 1 billion tons. This neutron star, only about 12 miles across, possesses a magnetic field trillions of times stronger than Earth's. As it spins, this magnetic field acts like a cosmic generator, accelerating particles that emit beams of intense radio waves from its magnetic poles. If the star's spin axis is misaligned with its magnetic axis, those beams sweep through space like the ray of a lighthouse. Each time a beam flashes across Earth, we detect a pulse. The object Bell Burnell discovered was not LGM-1, but the first known pulsar. The moment of realization was a profound pivot in human understanding. It marked the precise boundary where an interstellar enigma, a signal so perfect it whispered of minds beyond our own, transformed into a groundbreaking discovery of a new state of matter. The little green men were not calling. Instead, nature had built a clock of unimaginable density and power, a celestial mechanism more precise than any human invention. Jocelyn Bell Burnell's scruff on a chart became the key to understanding the violent aftermath of stellar death. Her discovery, for which her male supervisor later received a Nobel Prize, is a landmark not just in astronomy but in the philosophy of exploration. It teaches a humbling and exhilarating lesson. The universe is capable of producing phenomena so orderly, so seemingly designed, that they perfectly mimic the signatures we imagine for intelligence. The line between the unknown and the newly understood is not fixed. It is a frontier that shifts with every careful observation, every question mark in red pen, reminding us that the cosmos is stranger and more wonderful than any fiction. The perfect cosmic clock of a pulsar measures time, but time itself is running faster than anyone ever predicted. In the late 1990s, two independent teams of astronomers were using distant supernova as cosmic mile markers, hoping to measure how quickly the expansion of the universe was slowing down after the Big Bang. The result was a shock that overturned our fundamental view of cosmic destiny. They discovered the universe is not slowing down at all, it is speeding up. Some mysterious repulsive force, now called dark energy, is stretching the fabric of space itself at an ever-increasing rate. The evidence came from a specific type of stellar explosion, a Type 1, a supernova. These are known as standard candles because they always explode with nearly the same intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with great precision. By then measuring how much their light is stretched or redshifted by the expansion of space, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The data from supernova billions of light years away showed they were significantly fainter and thus farther away than expected in a universe whose expansion was coasting or breaking. The only explanation was that the expansion had been slower in the past, meaning it has been accelerating over the last several billion years. It was as if you threw a ball into the air and watched it not only fail to fall back down, but shoot away faster and faster into the sky. This discovery earned the teams the Nobel Prize and plunged cosmology into its deepest mystery. So what is this dark energy that makes up about 68% of the entire energy content of the cosmos? The leading candidate is the simplest yet most bizarre. It is a property of empty space itself. In Einstein's equations, there is a term called the cosmological constant, which represents a constant energy density inherent to the vacuum of space. This vacuum energy would exert a negative pressure, causing a repulsive gravitational effect that drives space apart. The problem is that when physicists try to calculate the expected value of this energy from quantum theory, they get a number that is 120 orders of magnitude too large. That is a 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. This staggering mismatch suggests we are missing something profound about the marriage of gravity and quantum mechanics. A more dynamic alternative is a field called quintessence. Unlike a constant vacuum energy, quintessence would be a kind of fluid or field that permeates space and can change very slowly over time. Its energy density could have been different in the early universe, potentially explaining other puzzles. Yet another, more radical idea is that our theory of gravity, Einstein's general relativity, is incomplete on the largest scales. Perhaps we do not need dark energy at all, but a modified understanding of how gravity works across cosmic distances. Each possibility leads to a different, ultimate fate for the universe. If dark energy is a true cosmological constant, the acceleration will continue forever. Billions of years from now, distant galaxies will be pushed away so fast their light can never reach us. Our observable universe will shrink to our local group of galaxies, and the rest of the cosmos will fade into an eternal, inaccessible darkness, a heat death where space is cold, empty, and silent. If dark energy is quintessence, its strength could increase, leading to a catastrophic big rip where even atoms are torn apart, or it could fade away, allowing gravity to possibly reassert control. The nature of dark energy is not a distant abstraction. It is the force writing the final chapter of all existence. It asks us what the void itself is made of, and whether the ultimate destiny of everything we see is an endless, accelerating drift into solitude. Dark energy writes the final chapter of the cosmos, but closer to home, the final chapter of our own solar system story may still contain a missing character. Far beyond the orbit of Neptune, in the cold, dark reaches of the Kuiper belt, a handful of icy objects are behaving strangely. They are not scattered randomly. Instead, their highly elongated orbits are mysteriously clustered, as if shepherded by an unseen hand. This is the indirect evidence for a hypothetical giant world astronomers call Planet 9. We have never seen it, but its gravitational signature is written in the paths of these distant wanderers. The orbits of these extreme trans-Neptunian objects are tilted and aligned in a way that is extremely unlikely to happen by chance. It is as if you dropped a handful of marbles on a vast floor and found they had all rolled to rest pointing in the same direction. Something must be organizing them. The leading explanation is a planet 5 to 10 times the mass of Earth, tracing a slow, colossal orbit hundreds of times farther from the Sun than our own world. At that distance, a single orbit could take 10 to 20,000 years to complete. A year on Planet 9 would span all of recorded human civilization. The search for this ghost world is a monumental challenge. It would be incredibly faint, reflecting only the barest sliver of sunlight, and its motion across the sky would be agonizingly slow. Astronomers are using the world's most powerful telescopes, like Subaru in Hawaii, to scan vast swaths of the predicted orbital path, pixel by meticulous pixel. They are looking for a single, dim point of light moving against the static backdrop of infinitely more distant stars. Yet, the Planet 9 hypothesis is not the only possible explanation for the orbital clustering. Some scientists propose that the collective gravity of many smaller Kuiper belt objects, a vast but unseen population of icy bodies, could produce the same shepherding effect over billions of years. It is a gravitational chorus instead of a solo conductor. Others suggest the data itself might be biased, that the peculiar orbits we have found so far are simply the ones easiest to detect from our particular vantage point on Earth. The quest to confirm or rule out Planet 9 is about more than just filling a blank spot on a solar system poster. It is a fundamental test of our understanding of planetary formation and dynamics. If it exists, Planet 9 would be a relic from the solar system's violent infancy, a core that formed among the giant planets but was flung outward during gravitational tussles with Jupiter or Saturn. Its discovery would rewrite the history of our cosmic neighborhood, revealing a dramatic reshuffling we never knew occurred. If it does not exist, then the strange orbital alignments point to something else entirely. Perhaps a flaw in our models of gravity in the outer solar system, or evidence for a previously unknown population of small, dark objects whose combined influence sculpts the void. Either outcome forces a revolution, Finding Planet 9 would mean our solar system harbors a giant, ancient exile, a frozen king of the distant dark. Ruling it out would mean the strange dance of the icy dwarfs is a clue to a different, equally profound mystery. The search continues, a patient sweep of the deepest cold, looking for the shadow that may or may not be there. The search for a hidden planet tests our models close to home, but a faint smudge of light in a distant telescope challenged the very bedrock of cosmology. In 2018, astronomers announced the discovery of a galaxy that should not exist. Catalogued as NGC 1052DF2, it was an ultra-diffuse galaxy, a ghostly, wispy collection of stars so thinly spread you could see right through it. But its true shock was not its transparency. When scientists measured the motions of 10 globular clusters orbiting this galaxy, they found them moving surprisingly slowly. According to the laws of gravity, the visible mass of stars in the galaxy was just enough to hold those clusters in place. There was no room left for the invisible gravitational glue of dark matter. This galaxy, they claimed, contained virtually none. The announcement sent seismic waves through the astrophysics community. For decades, dark matter was not just a theory, it was the essential scaffold for all modern galaxy formation. Every galaxy we had ever studied, from majestic spirals to tiny dwarfs, was embedded in a massive halo of this unseen stuff. Its gravity was the only thing that could explain how galaxies held together and how they formed in the first place. NGC 1052DF2 was an existential anomaly. If one galaxy could exist without dark matter, then perhaps dark matter was not a universal ingredient. Maybe our entire understanding of gravity was wrong, and this ghostly galaxy was the first clear evidence for an alternative like modified Newtonian dynamics. The debate was immediate and intense. Skeptics proposed a dramatic natural explanation. Perhaps the galaxy did form with dark matter, but it had been violently stripped away. It resides near a massive elliptical galaxy, NGC 1052. A close gravitational encounter could have torn the dark matter halo away, leaving behind the delicate stellar population, like a tree losing all its leaves in a storm while the fragile blossoms remain. Others questioned the measurements themselves. The key to the puzzle was the galaxy's distance. To calculate the mass needed to hold the globular clusters, you must know exactly how far away the galaxy is. The initial study placed it about 65 million light-years away. At that distance, the star motions made sense only if dark matter was absent. But science is a self-correcting process, and other teams rushed to make their own observations. Using more precise methods with the Hubble Space Telescope, a separate group measured the distance again. Their result was different. They placed NGC 1052DF2 much closer, at around 42 million light-years away. This change, while it might sound small, altered everything. At the closer distance, the galaxy's stars are intrinsically fainter. This means there is less visible mass than originally thought. Suddenly, the slow-moving globular clusters were not held by the stars alone. They required the extra gravitational pull of a substantial dark matter halo after all. The enigmatic galaxy without dark matter began to look much more ordinary. Later studies of the galaxy's stellar population supported this, finding it was older and more evolved than first estimated, consistent with a galaxy that had indeed lost much of its gas and possibly had its dark matter halo disturbed but not completely removed. The story of NGC 1052DF2 is a powerful lesson in scientific humility. It was not a fatal blow to the dark matter paradigm, but a rigorous stress test. The initial anomaly was so profound it forced everyone to re-examine their assumptions, their methods, and their measurements. The follow-up scrutiny did not destroy the mystery, it refined it. We learned that ultra-diffuse galaxies are fascinating laboratories where the relationship between stars and their dark matter halos can be stretched to extremes. The episode highlights how true enigmas in interstellar space are not dead ends. They are invitations to look deeper, measure more carefully, and question more thoroughly. The universe presents us with puzzles not to confuse us, but to compel us to see more clearly. Each strange signal, each anomalous orbit, each ghostly galaxy is a question. And the relentless, collaborative pursuit of the answer, even when it corrects our most exciting mistakes, is what slowly turns the darkness into understanding. From the faintest whisper of a radio signal to the silent, accelerating push of dark energy, these 25 enigmatic events are more than just cosmic curiosities. They are the frontiers of our understanding, the places where the map of reality ends and the territory of the unknown begins. We began with a single, powerful WOW scribbled on a printout, a moment of pure possibility that launched a century of listening. We witnessed stars dim in impossible ways, objects tumble through our solar system from other suns, and bursts of energy so fierce they outshine galaxies. We followed the ghostly tug of unseen flows, stood before the cosmic void of Boötes, and traced the cold, dark nurseries where new stars are born. We met stellar corpses spinning perfect time, planets of diamond forged from stellar cannibalism, and the haunting, geometric art of dying suns. Each mystery, whether ultimately solved like the Pioneer anomaly or still unfolding like the nature of dark matter, represents a fundamental question asked of the universe. And with every question, humanity builds a better tool to seek the answer. The search itself is the engine of progress, driving us to launch more sensitive telescopes, to build deeper underground detectors, and to write more elegant equations. This journey does not end here. The next generation of eyes on the cosmos is already opening. The Vera C. Rubin Observatory will scan the entire visible sky every few nights, catching the fleeting and the variable. The James Webb Space Telescope peers deeper into infrared secrets. Future missions will directly image exoplanets and listen for gravitational waves from the dawn of time. Each new instrument is a key designed to fit a lock in the cosmic door. So as you look up at the stars tonight, remember that the darkness between them is not empty. It is full of questions waiting for their moment to be heard. Which of these 25 enigmas captivated you the most? Was it the lonely diamond planet, the runaway black hole, or the profound silence of the Fermi paradox? Let us know in the comments below. If you enjoyed this journey to the edge of understanding, be sure to subscribe for more explorations into the fabric of reality. The universe's greatest stories are still being written, and the next chapter is always just over the horizon. Keep looking up.